Now let's discuss the EEPROM abstraction interface. This is denoted by EA, which stands for EEPROM abstraction interface. It provides services for reading, writing, erasing data to and from EEPROM memory. This EA provides abstraction from the addressing scheme of underlying EEPROM driver and hence provide a uniform addressing scheme to the upper layer. So basically, EA is part of the abstraction part where we are actually communicating to MMF and also to the EEPROM driver. So EA acts as the mediator here and it provides an addressing scheme which is uniform to the above layers. It ensures that the upper layer, that is, after MMF it comes the NVM, need not be changed if the underlying EEPROM driver and device is replaced. So that's how we are keeping NVM independent of the hardware. Now the EEPROM abstraction interface provides a 32-bit virtual linear address space and uniform segmentation scheme. Okay, so this is what is provided to the MEMF. So what is provided? It provides a 32-bit virtual linear address space. And since it's uniform, it's very easy to access different addresses. Now, this virtual 32-bit address range consists of two parts. One is the 16-bit block number and another is the 16-bit block offset. The 16-bit block number allows theoretically 65,536 logical blocks, and the block offsets allows a theoretical block size of 64 kilobytes per block. So with combination of both of this, the virtual 32-bit address is established by the EA module. Now the 16-bit block number represents a configurable paging mechanism. Okay, the value for this address range can be derived for that of underlying EEPROM driver device. And this virtual paging is configurable by the parameter EA virtual page size. So that's all. We can configure it depending on the underlying EEPROM driver, and the virtual paging is configured using the parameter EA underscore virtual page size. Now let's look at the EA related APIs. The first one is EA read, which reads the length bytes of block number at block offset into the buffer data buffer pointer. So this is the API which is used to perform the read operation, and it will take in consideration the block number and the block offset and to the buffer pointer, which is data buffer pointer. Next is EA write API. This writes the contents of the data buffer pointer to the block number. Next API that is available is the EA job end notification. So this notification will report the module if the module is successfully ends the asynchronous operation. So one of the operation has ended successfully, then this notification will be called. The next API is EA job error notification. This reports the failure of an asynchronous operation. So if some operation was happening and it failed, then this notification will be called. Next is EA main function. It is in EA main function the requested jobs and internal management operations are performed. So we need to schedule this main function, and it is here the requested jobs and the internal management operation are taking place. The cycle time of this main function should be same as that configured for the underlying EEPROM driver. So if the driver is being called in 5ms, then we have to configure the EA main function to be also be at the same cyclicity. So that's all about EA module. Now we'll look at Phi module. So Phi stands for Flash EEPROM emulation. It provides virtual addressing scheme and virtualization. Since it's providing a virtual addressing, it abstracts the actual hardware, that is physical addressing. It abstracts from device a specific addressing scheme and segmentation. This provides the upper layers with a virtual addressing scheme segmentation as well as virtually unlimited number of erase cycles. So due to this virtual addressing scheme, very similar to what we saw in EA, because we will get virtually unlimited number of erase cycles. Now Phi is used to access underlying flash memory. Phi uses FLS driver to read or write data from and to the flash memory. Call from NVRAM manager is passed to Phi module and Phi to FLS. This Phi provides services to read and write the block. So it's simple. The NVRAM manager is there, the MEMIF is there, then the Phi module will be used to communicate with FLS, and this will be able to perform read and write operation. And all this will be done through the virtual address range that is provided to the NVM, and this addressing scheme is provided to NVM and NVM will act upon it. But finally we will convert it into the physical addresses and it will be then control the FLS. Now again, similar to EA, we have 32-bit addressing scheme, and this address is divided into 16-bit block number and 16-bit block base number. The 16-bit block number allows total of 66,535 blocks, and the block offset allows 64 kilobytes per block. Now the 16-bit block number represents a virtual block, and virtual block is made up of virtual pages. So at the start of the course we spoke about pages, right? And this is what is the use of these pages. Here the virtual block is made up of virtual pages. So Phi virtual page size is a configuration parameter used to configure the virtual page size. So if we set this parameter, we will be able to configure the actual page size. The virtual page size should be multiple of physical page size. So this is what we should be careful about. Physical page size depends on underlying flash memory. Example, if a block is of size 32 bytes and the Phi virtual page size is 8 bytes, then 4 virtual pages are required for the block. And if size of 52 bytes, then we'll need virtual pages required, that is required are 7, then we need 56 bytes. So this is the way we need to understand how the virtual paging is done. Now Phi calculates physical address from block number and block offset. Okay, let's look at the read and write block using Phi. So similar to EA, here we have Phi read operation, and this is for initiating a read job. The block offset and block number are provided as input parameters to Phi read. And using block offset and the block number, Phi will calculate the actual physical address. So these two parameters are used to get the actual physical address. Similarly, Phi write function is used for initiating write job. So function Phi write takes the block number as input parameter, start address, and calculates the corresponding memory write address. Another parameter, Phi number of write cycle, decides number of write cycles for the logical block. So here we will be able to configure how many write cycles are available for the logical block. Now, fee main function is also another important function, and this is handling the read, write, erase job request asynchronously. Similar to EA module, we have notification functions here. The first one is the job end notification, which reports successful end of asynchronous request. The underlying flash driver will call this notification function. Another notification function is the job error notification. It is used to report the failure of an asynchronous operation. If some failure occurs, this notification is called. So that's all about EA and fee modules. In next session, we will discuss about the driver modules, which are FLS and the EEPROM.